Welcome to the General Chemistry 2 class. This section is on chemical equilibrium. This lesson is about solving problems on chemical equilibrium, focusing on predicting equilibrium shift and calculating equilibrium constants. Let's begin. In this lesson, we will calculate equilibrium constant under pressure or concentration of reactants or products in an equilibrium mixture. Example number 1. In a reaction vessel, 0.350 molar ammonia was heated to 820 Kelvin, and the following reaction took place. 1 mole nitrogen reacting with 3 moles hydrogen to produce 2 moles ammonia. Determine the shift of the equilibrium given that equilibrium constant equals 0.024. So this is our solution. Our working equation is the corresponding reaction quotient value for the reaction. Vessel contains only the product, thus reaction quotient is indeterminately large. This value is much greater than the equilibrium constant. Thus, the equilibrium shifts to the left, towards the formation of nitrogen and hydrogen. Example number 2. A reaction vessel consisting of 0.20 molar each of nitrogen, hydrogen, and ammonia was heated to 820 Kelvin to allow the reaction in example number 1 to take place. Given that equilibrium constant equals 0.024, determine if these concentrations are at equilibrium. If not, determine the shift of the equilibrium. So this is our solution. Our working equation is the corresponding reaction quotient value for the reaction. Let us substitute the initial concentration values, and we get reaction quotient equals 25. Comparing this to the equilibrium constant value, which is 0.024, we see that reaction quotient is greater than equilibrium constant. Since reaction quotient is greater than equilibrium constant, the equilibrium shifts to the left, towards the formation of nitrogen and hydrogen. Example number 3. For the reaction of 1 mole nitrogen with 3 moles hydrogen forming 2 moles ammonia, the equilibrium concentrations of the reactants and product at 350 degrees Celsius are as follows. Nitrogen concentration equals 0.99 molar, hydrogen concentration equals 0.30 molar, ammonia concentration is equals to 0.40 molar. Calculate the value of equilibrium constant for the reaction. So this is our solution. We first write the equilibrium constant expression for the reaction. Afterwards, we substitute the given equilibrium concentrations. Take note that units may not be shown in the solution. The value of equilibrium is 6.0. Let us derive the equation showing the relationship of equilibrium constant and the equilibrium constant for partial pressure. From the ideal gas equation, the partial pressure of a gas can be converted from its concentration. The partial pressure equals molar concentration times the gas constant R times temperature T. Thus, for the reaction of nitrogen and hydrogen yielding ammonia, the equation for equilibrium constant of partial pressure becomes equilibrium constant of partial pressure equals equilibrium constant times quantity RT raised to the exponent -2. In general, equilibrium constant can be converted into equilibrium constant of partial pressure according to the following equation. Equilibrium constant of partial pressure equals equilibrium constant times quantity RT raised to the exponent delta Ng. R is the universal gas constant equals 0.021 liter times atmosphere per mole Kelvin. T is the temperature in Kelvin, and delta Ng equals sum of coefficients of gaseous products minus sum of coefficients of gaseous reactants from the balanced chemical equation. Example number 4. Convert the calculated equilibrium constant in example number 3 to equilibrium constant of partial pressure. So this is our solution. Let us use the equation for equilibrium constant of partial pressure that we derived earlier. Substitute the given equilibrium constant. Note the temperature must be in Kelvin, so the given temperature, 350 degrees Celsius, must be added to 273.15. Simplifying the equation gives us equilibrium constant of partial pressure equals 2.3 times 10 raised to negative 3. Example number 5. A reaction vessel initially contained 0.25 molar nitrogen dioxide and the following reaction was allowed to take place at 25 degrees Celsius. 2 moles of nitrogen dioxide reacting reversibly to form dinitrogen tetroxide. At equilibrium, the concentration of dinitrogen tetroxide was found to be 0.057 molar. Calculate the value of equilibrium constant for the reaction. So this is our solution. Start from calculating the reaction quotient. Since no product is initially present, the value of reaction quotient is obviously 0. Even though the value of equilibrium constant is not yet given to us, it is logical to think that the equilibrium shifts to the right or towards the formation of dinitrogen tetroxide. Let us tabulate the concentrations of the reactant and product before and at equilibrium. Initially, the concentration of nitrogen dioxide is 0.25 molar, while there is 0 concentration of dinitrogen tetroxide. The reaction proceeds by producing dinitrogen tetroxide while consuming nitrogen dioxide. Let X be the concentration of dinitrogen tetroxide produced until equilibrium is reached. If X is the concentration of the product formed, 2X is the concentration of the reactant. The coefficient 2 is based on the balanced chemical equation. We use plus sign to denote formation while minus sign to denote consumption. Next, we add the initial concentration and the change in concentration to get equilibrium concentration for each substance. For nitrogen dioxide, the equilibrium concentration equals 0.25 molar minus 2x. The equilibrium concentration of dinitrogen tetroxide is already given in the problem, which is 0.057 molar. We can solve for X since the equilibrium concentration of dinitrogen tetroxide is given. Again, initial concentration plus change in concentration equals equilibrium concentration. 0 plus X equals 0.057 molar. Solving for X, we get 0.057 molar. On the other hand, the concentration of nitrogen dioxide at equilibrium equals 0.25 molar minus 2x. Substituting the value of X, we obtain nitrogen dioxide concentration equals 0.136 molar. Lastly, we write the equilibrium constant expression for the reaction. Equilibrium constant equals concentration of dinitrogen tetroxide divided by the concentration of nitrogen dioxide squared. Substituting the equilibrium concentration values, we get equilibrium constant equals 3.1. Example number 6. A vessel heated to 600 Kelvin contains a mixture of nitrogen dioxide and sulfur dioxide, both with partial pressure of 5.00 atmosphere. These gases react according to the following equation. At equilibrium, the partial pressure of nitric oxide was found to be 4.73 atmosphere. Calculate the equilibrium constant of partial pressure for the reaction. This is a solution. Let us tabulate the partial pressures before and at equilibrium. Initially, nitrogen dioxide and sulfur dioxide are the gases present, both with partial pressure of 5.00 atmosphere. On the other hand, nitric oxide and sulfur trioxide are initially absent. Without calculating the reaction quotient, it is obvious that the shift of the equilibrium is towards the formation of nitric oxide and sulfur trioxide since they are initially absent. If we let X be the concentration of nitrogen dioxide consumed, X will be also the concentration of sulfur dioxide consumed and the concentrations of nitric oxide and sulfur trioxide produced. Again, the negative sign in the change in partial pressures denotes consumption while positive sign denotes formation. The equilibrium partial pressure is the sum of initial partial pressure and the change in partial pressure. For nitrogen dioxide, the equilibrium partial pressure is 5.00 atmosphere minus X. The same goes for sulfur dioxide. For sulfur trioxide, the equilibrium partial pressure equals X. For nitric oxide, it is 4.73 atmosphere. Focusing on the box portion of the table, we have 0 plus X equals 4.73 atmosphere. Solving for X gives us X equals 4.73 atmosphere. Substituting X in the obtained expression for equilibrium partial pressures, we obtain the following values. For nitrogen dioxide and sulfur dioxide, 0.27 atmosphere. For sulfur trioxide, 4.73 atmosphere. We can now calculate the value of equilibrium constant of partial pressure given the calculated partial pressures. From the equilibrium constant of partial pressure expression for the reaction, substitute the calculated partial pressures accordingly. Simplifying give us equilibrium constant of partial pressure equals 307. To summarize, the shift of equilibrium can be predicted from the reaction quotient, which can be calculated from the initial concentrations or partial pressures. It is helpful to tabulate the concentrations or partial pressures of reactants and products and account how these values change to reach equilibrium in order to calculate the equilibrium constant. Here are the references or bibliography for further readings. That will be all. Thank you.